Yes, I'm audible.
Good afternoon, sir.
Yes, good afternoon. Yeah, last we have discussed in a topic in physical. Yes, I'm right.
Yes, we have discussed about the Boltzmann distribution in the rotational spectroscopy.
Yes, I think it's a role of Boltzmann distribution in Gmax value. Yes.
Yes, sir.
Yes, carry on.
Yes, sir. The Boltzmann distribution has a major role in deciding the Jmax value or deciding the level for which the population of rotational levels is highest. So, according to Boltzmann distribution of for a rotational uh, uh, for a rotational spectroscopy, the ground state is not a most populated state, and we see that the population of a rotational energy level is highest in some J value, which is denoted as a Jmax value. So we can find this Jmax value by applying a maxima condition to this particular Nj upon N naught, which is a Boltzmann population ratio. And by applying a maxima condition, we can find the Jmax value. So according to Boltzmann distribution, we know that the Nj upon N naught, which is the population in the Jth state upon the population in the ground state, is equal to the 2j plus 1 in bracket and into e to the power minus bj plus 1 by kt. So here my bj plus 1 represent the energy difference of the jth state and the originally the ground state, and 2j plus 1 represent the degeneracy of the jth state. So for a ground state, we have a degeneracy is equal to 1, and the energy corresponding to the ground state is 0.
Yes, good. Yeah, next one is polyatomic molecule. Yes, what the main purpose
Yes.
of polyatomic molecules in rotation spectra?
Yes, sir. So, polyatomic molecules, so rotation in polyatomic molecules enable us to study the rotational properties or the bond length or bond angle or the mass of the polyatomic molecule during the rotation of a molecule. So polyatomic molecules lead us to study about the more realistic molecules. Sir, in general, as we have studied all the models for the rotational spectroscopy, we only applied it to, or we only limited it to the diatomic molecules. So the extension of model to to study the extension of model of a diatomic to study the polyatomic molecules can enable us to study the properties of a polyatomic molecule. So polyatomic molecules, they are basically divided into four parts, and these four parts are divided on the basis of the moment of inertia associated with the three axes, that is x, y, z. Here we represent it by a IA, IB, and IC. So the four type of molecules we have is the spherical molecule. Then we have a linear molecule, and then we have a symmetric molecule, and at last we have a asymmetric molecule. So symmetric molecule are further divided into two parts, which is a prolet molecule and a oblet molecule. Now, sir, coming with the spherical molecule. So spherical molecule has the all the three moment of inertia along with the three directions, it is equal to each other, and we see that there is a no activity, or there is a no change in the dipole moment in the spherical molecule, and we see that the molecule is inactive in a rotational spectroscopy. And for linear molecules, sir, we have one of the moment of inertia along one direction is equal to 0, and two of the moment of inertia are equal to each other. So, sir, in that case, what we have, we have the diatomic case. So the linear molecule is just the extension of a diatomic molecule, diatomic molecule model that we have studied earlier. So only in a diatomic molecule will be use high in case of linear molecule, and apart from that, the spectra is very similar to that of the diatomic molecule. Now, so the third we have is a symmetric molecule. So in symmetric molecule, we have two cases. So in symmetric molecule, we have a two moment of inertia is equal to each other, and we have a third moment of inertia along the third direction. It can be greater than, or it can be less than that of the other two. So on the basis of the greater than or the less than the other two, we have a two category. So first is the prolet. So in prolet, we have a IA is equal to IB, and the another one is IC, and we see that the IC is less than that of the IA and IB. So example of this type of molecule can be considered as a molecule. Now, leading to the second time, which is a oblet molecule. So in oblet molecule, we have a two moment of inertia, that is IA is equal to IB, and the third, that is IC, it is greater than the those two, and we see that in this type of molecule, the example is the benzene shows the activity, or shows the this type of oblet symmetry in its molecular structure. And so at last we have so both the symmetric molecule shows activity in a rotational spectroscopy. So at last we have a asymmetric molecule. So in asymmetric molecule, we have all the three moment of inertia along all the three direction. It is not equal to each other, and we see that these type of molecule are also shows activity in rotational spectroscopy. So only the thing is that there exists a complexity in the calculation of the moment of inertia for the asymmetric molecule. So we usually do not study these type under the rotational spectroscopy.
Yes. What the main purpose of polyatomic molecule in rotational spectra and spectroscopy?
So can you please repeat the question?
Yes. What the main purpose of polyatomic molecules in rotational spectra and spectroscopy?
Yes, sir. So the main purpose is to extend our knowledge about the diatomic molecule model of rotational spectroscopy to the larger scale of the molecule. As we are only dealing with the molecule which has a two atoms. Sir, in case of polyatomic molecule, we have a more than two atoms, and so the polyatomic molecules enable us to study the more real scenario than the what we have studied by the experimental model or the ideal model that we have studied. And apart from that, sir, if we take the case of a symmetric rotor, for example, we have a prolet type, that is CH3Cl. So we see that the in a rotational spectroscopy, we are able to define the change of the rotational energy or the energy level of the rotational level of a prolet molecule. So these energy can be defined as the energy expression is equal to the E is equal to BJJ plus 1, then BJJ plus 1 minus A plus A minus B in bracket K into K plus 1. So this K represent the angular momentum along one direction or along one of the moment of inertia that we have, and the J represent the total angular momentum, and K represent the angular momentum along one direction. Now, sir, A here represent the it also represents the rotational term only, but the only difference is that we have a principal axis. So the A here represent the moment of inertia along the principal axis that is involved, and the B here represent the moment of inertia associated. I'm so sorry. B here represent the rotational constant that is associated with the other axis that generates a moment of inertia.
Yes, good. Next is Raman spectroscopy. Yes, what the basic application of Raman?
So, Raman spectroscopy, it talks about the scattering phenomenon, and sir, it enable us to study the properties of a homonuclear diatomic molecules, which we see in most of the spectroscopic techniques. It is not very useful to use, like in like in microwave or the vibrational spectroscopy. We see that the homonuclear diatomic molecule does not fulfill the selection rule, and it shows no activity in these type of spectroscopy. So we use a Raman spectroscopy to study the molecular properties such as bond angle, bond length, and the uh, uh, frequency of a bond that is involved in a homonuclear diatomic molecule. So one of the major application arises from Raman spectroscopy is to study the vibrational properties of a O2 molecule. So the binding, sir, in most of the bioinorganic complexes, we see that the O2 transportation is very much useful phenomenon in the human body and also in invertebrates. So the differentiation of the O2 bonding in a human body and in an invertebrate can be distinguished by studying the vibrational frequency of O2 in a Raman spectroscopy. And sir, at last we are able to study the aqueous sample under the Raman spectroscopy. Sir, as we know that the vibration spectroscopy comes in our mind mostly when we talk about the functional group when we talk about the detection of a functional group. But in most of the sample, it is not very useful as H2O molecule hinders the peaks in a air, and it shows a activity in a vibration spectroscopy. While if we go for the Raman spectroscopy, we see that there is a weak signal for H2O, and we can easily analyze our sample rather than getting hindered by the H2O peak.
Yes, good. Raman spectroscopy selection rule del J is equal to 0, plus minus 2 for rotational spectra. In vibrational spectra, harmonic and harmonic, del V is equal to plus minus 1. And harmonic is del V is equal to plus minus 1, 2.
Sir, your voice is breaking.
Yes, I'm audible now.
Yes, sir.
Yes, Raman spectra selection rule for rotational is del J is equal to 0, plus minus 2. Yes, I'm right.
Yes.
Yes, how to drive it? Why is 0, plus minus 2? Why is not
Yes, sir.
0, plus minus 1 plus minus 2 in
Yes, sir.
rotational spectra?
So, when we see the selection rule for rotational Raman transitions, we see that the selection rule, that is delta G is equal to 0, plus minus 2. So here the 0 represent the Rayleigh transition, a Rayleigh transition or a Rayleigh line, which arises from the elastic scattering of a light from a molecule. And coming to the plus minus 2, sir, here plus 2 represent the Stokes line or the absorption. So, sir, this plus minus 2 is solely dependent on the symmetry of a rotational molecule, and it arises from the symmetry of a rotational molecule. So, generally, we have an electric field vector associated with the radiation that we are using, and we see that the molecule which is rotating or molecule which is active in a Raman spectroscopy, it shows the interaction with this electro it it shows interaction with this electric field, and we see that the rotation is restored after the rotation is restored after the molecule rotate 180 degree. So this plus minus 2 arises from that, as a molecule rotates 2 times 180 degree, and it comes back to its original position. And sir, it is also dependent on the polarizability of the molecule. Sir, during a polarizability, the molecular symmetry changes as the molecule get polarized into plus and minus charges during the interaction with the radiation. So this restoration of this restoration or this restoration of the symmetry during the polarizability, it leads to the arise of the leads to the arise of the selection rule for the rotational spectroscopy. Sir, am I audible?
Yes, yes, yes. What the
Yes.
selection rule for vibration Raman spectrum? Harmonic and harmonic? Any other?
Yes, sir. So, when we see for the vibration spectroscopy, in case of a simple harmonic oscillator, we have a selection rule as a delta V is equal to 0 plus minus 1. So, here delta V is equal to 0 represent a Rayleigh line, while plus minus 1 represent the Raman lines. And sir, when we talk about the enharmonic oscillator, we have a selection rule that is delta V is equal to 0 comma plus minus 1 comma plus minus 2 plus minus 3 and so on. So here 0 represent the Rayleigh line, while the uh, plus minus 1 plus minus 2 plus minus 3 plus minus 4 represent the selection rule with respect to the enharmonic oscillators.
Yes. Next is PQR branch, rotation and vibration Raman spectra. And Stokes line,
Yes, sir.
anti-Stokes line, and Lilly lines. Yes. What is the any similarities and difference of these one?
Yes, sir. So when we see the spectra for the rotational Raman transition, and when we spectra, that is it contained the Rayleigh line, and it also contained the Stokes value, and it also contained the Stokes line and anti-Stokes line. So Stokes line has slightly higher energy as comparison to the Rayleigh line, and anti-Stokes has a lower energy as compared to the Rayleigh line. So, and if we see for the vibrating rotor, that is it consists of a PQR branch. So in that case also we see a similar spectra arises. That is, we have in the middle we have a Q branch, which arises from the delta G is equal to 0 transition. And then we have at the right side, we have a R branch, which arises from delta G is equal to plus 1. And the left side, we has a delta G is equal to minus 1, which belongs to the P branch. So this spectra of vibrating rotor and the rotational Raman is very similar in terms of the nature of the spectral lines. So only difference is that In rotational Raman, the transition arises from the inelastic collisions. So the anti-Stokes and Stokes line are weaker as comparison to the P and R branch that we have seen, and the Q branch in case of the vibrating rotor is tends to have a low intensity as comparison to the relay line. Relay line generally has a very huge intensity as comparison to the other lines. Now, sir, the another difference is that the selection rule which arises. So in case of a vibrating rotor, we have a selection rule for a rotational transition, that is delta G is equal to 0 and a plus minus 1. So here a plus minus 1 represent the R branch and P branch respectively. And if we go for the rotational Raman, we see that the selection rule is equal to delta J is equal to 0, comma plus minus 2. And apart from this, sir, the separation between the lines are also not equal, and this shows a difference in the separation of a lines shows a different value. So in case of a Raman, rotational Raman, we have a separation between the each Stokes and anti-Stokes line as a 4B difference between the each anti-Stokes and each Stokes line within the Stokes line only. And when we see the difference or the separation between the Rayleigh line and the Stokes line, or Rayleigh line to the anti-Stokes line, we see that the difference is a 6B. Now, so when I move to the vibrating rotor, in that case, the separation between the lines is of the 2B separation. That is the difference or separation between the within the R branch or Q branch. The line separation shows as a 2B, and separation between the Q branch and the R branch or Q branch to the P branch, we see the separation is 4B.
Yes, how many factors affecting to PQR branch and Stokes, anti-Stokes and relay lines?
Yes, sir. So, I'll talk with the anti-Stokes and Stokes line. So, anti-Stokes and Stokes line, sir, they are solely dependent on the excitation wavelength. That is the light that we are using for the excitation, or for the during the interaction or during the scattering process. So that the lines are dependent on that, and the energy of Stokes and anti-Stokes line are defined by considering the energy of the exciting wavelength. Now, when we talk about the PQR branch, we see that it is dependent on the band origin, or it is dependent on the vibrational frequency for the vibrational energy change for the fundamental vibration. So generally we denote it with the nu naught, and it gives that nu naught is equal to nu gives a nu E bar, that is a harmonic oscillator frequency for an enharmonic oscillator. That is the equilibrium frequency for enharmonic oscillator, and then in bracket we have a 1 minus 2 Xc. So these branches are dependent on the enharmonicity constant, as well as on the equilibrium frequency of the vibration or a vibrating rotor. And sir, these are also dependent on the symmetry factors. That is, if we talk about the Q branch, the appearance of Q branch, sir, in case of linear molecule, we see that the Q branch does not appear. And when we talk about the molecule which has a odd electron in it, then in that case we see that there is a appearance of a Q branch. While sir, anti-Stokes and Stokes line, in sir, in this case also we see the effect of symmetry is there. as the selection rule or the first condition to the appearance of a Raman spectroscopy is that molecular polarizability must change. So whether if a molecule will have a polarizability change during the interaction, then we see the appearance of these lines. If it does not have the change in the vibrational, it does not have a change in the polarizability of the molecule. In that case, we do not see the appearance of Stokes and anti-Stokes line.
Yes. Okay, next move on electronic spectra. Yes, what the selection rule of
Yes, sir.
electronic spectra? Now how to drive it, how to find.
Sir, so what you have said after the selection rule, I was only able to hear the half question.
Yes. Electronic spectra. Yes, what the selection rule of electronic spectra and how to drive it, how to find selection rule of electronic spectra. Describe.
Yes, sir. So electronic spectra has a two selection rule, which deals with the spin of the electron that is involved in the transition, and another deal with the parity or the symmetry of orbital that is involved in the electronic transition. Sir, according to spin selection rule, the delta S should be equal to 0, and according to the parity selection rule or Laporte selection rule, we see that the delta L is equal to 0 or plus minus 1 if we talk about the if we talk about the molecule. Now, sir, uh, the spin selection rule tells us that when a transition occurs from a electronically ground state to the electronically excited state, the spin of the molecule should remain changed. That is, if it is a upspin, in the excited state also, it must possess the upspin only. And if it has a downspin in the excited state, it must possess a downspin only. And the second, if we talk about the parity selection rule, sir, it talks about the symmetry of the orbital that is involved in the transition. Sir, according to this, if a ground state is a gerad, then the excitation of a molecule to the excited state will only happen if we have a excited state with the ungerad symmetry, and vice versa. And if we see the similar, uh, we have a similar symmetry in the ground state and excited state, so those transitions are termed to be forbidden for the electronic transition. And so apart from this, we see that these transitions are highly dependent on the Frank-Condon factor, and the intensities of these transitions are highly dependent on the Frank-Condon factor, which talks about the quantum mechanical which talks about the quantum mechanical behavior of interaction of electromagnetic radiation with the electronic transition, and the consequences of the transition dipole moment, which is interacting during the electronic transition of the molecule. So the electronic transition originate when we have a UV visible light. It is it is made to be fall on a molecule, and the molecule absorbs a UV visible light, and it gets excited from a ground electronic state to the higher electronic state. So this is the origin of a electronic transition. And so these transition can also be explained with the help of Beer-Lambert's law, which talks about the dependence or the intensity of a light, or the absorbance of a light on the concentration of a molecule. So if we have a higher concentration of a molecule, we generally see that the absorption is tends to be higher in that case.
Yes, good. You talk about the Frank-Condon principle.
Yes, sir.
What the role of quantum mechanics, wave function, intensity, flipping of The Frank-Condon principle.
Yes, sir.
Describe it.
Yes, sir. So, the electronic transition that occur, sir, according to Frank-Condon principle, it is stated that during the electronic transition, the electronic transition tends to be very fast. That excitation of the electron from ground state to excited state is very fast, and due to which we see that there is no appreciable changes occur in the nuclear coordinates when we see when we see the electronic transition happening. And sir, Frank Condon principle also talks about the intensity intensity of the transition that is happening, and also it accounts the effect of a quantum mechanical wave function quantum mechanical wave function and its interaction with the UV visible radiation during the transition that is happening. Sir, according to Frank Condon principle, the intensity of the transition can be predicted by the Frank Condon factor, which talks about the which talks about the two factor. So basically, the integral or the transition moment integral, it is composed of a two factor. One is the Frank Condon factor, and another is the transition moment dipole integral. So the transition moment dipole integral, sir, it talks about the interaction of UV visible light to the UV visible light to the molecule, and the how the molecule interact and how the excitation happens. And sir, another we have is the Frank Condon factor. So Frank Condon factor basically takes account in the vibrational wave function that is occurring as the vibrational transition are occurring during the electronic transition. And according to Frank Condon factor, we see that the vibrational transition happens from a vibrational ground state to those excited state to those excited state whose wave function are equally symmetric, or whose wave function are completely overlaps, or whose wave function are completely resembles the ground state wave function. Sir, it talks the it talks this interaction in terms of the probability density function, uh, and the how the interaction of two wave function occur during the transition.
Yes, good. Yes, any role of spectroscopy? Carbon-13 NMR and another 1HM, any other spectroscopy used in Frank-Condon principle?
Sir, can you please repeat the question?
Yes, any role of spectroscopy in Frank-Condon principle? 1H NMR, carbon-13, 19F, 31P, any role?
So, Frank Condon principle, sir. Sir, one of the major application is that it explain us the Heisenberg uncertainty principle. So that it talks about the lifetime. It talks about the electronic lifetime that is occurring during the change in a during the excitation of a molecule. And apart from that, sir, it also considered that the electron cloud around the molecule or around the nucleus of an atom which is involved, it changes during the transition. So which is due to which we see there is a change in a dipole, and we see that we see that it can produce an oscillating or propagating field associated with these dipole, so which can be very helpful in so when we talk about the NMR, So, generally the field that is associated with the electromagnetic radiation, sir, it can have a two components, and that is magnetic and electrical. So, if the electron cloud changes, so it may be possible that it can change the magnetic field component of a propagating field which is produced during the electronic transitions.
Yes, good. Yeah, next move on chemical kinetics. Chemical kinetics is what the main role of, yes,
Uh,
daily life example of chemical kinetics.
so we have a several example in a for a chemical kinetics. Suppose we see the burning of a paper. In this combustion reaction happens, and we see that the this reaction is very fast. Or if we talk about the evaporation of a water molecule, so we see generally these type of reaction are very fast, and they happen in a flip of a second. So, sir, this can be seen that the as example of a chemical kinetics as a the rate for these type of reaction is very fast, and we can say that the uh, we can study this type of reaction under the chemical kinetics, and we can predict whether the rate is fast or slow. So generally this reaction has a faster rate, and this we can predict with the help of chemical kinetics.
Yes, chemical kinetics is order of reaction. What the difference between
Yes, sir.
order of reaction and law of thermodynamics? What the basic difference?
The order of reaction uh, refers to a power with which a concentration is raised in a rate law equation. So in a rate law equation, we have a rate is equal to K into concentration of reactant to the power some n value. So this n value represents as the order of the reaction. Sir, it talks about the order of a reaction tells us about the dependence of a rate on the concentration. Sir, for example, if we take a n is equal to 1, so then we say that the rate is directly proportional to the concentration to the power 1, and the order of reaction is termed as a first order. And so the order of reaction can be fractional, it can be zero, and it can be a negative value. Uh, Now, on the other hand, if we talk about the laws of a thermodynamics, sir, laws of a thermodynamics, it consists of four major laws that governs the thermodynamic properties or the change of the energy or temperature that we generally see. So in this we have a first law, second law, third law, and we have a zeroth law. So these all type of law talks about the different properties of the or different form of the energy which is involved. So the zeroth law explains us that the energy uh, energy is the neither become destroyed or it neither be produced. It can only be converted from one form to another. Sir, in chemical terms or in terms of a substance, we can say that if a molecule A is in equilibrium, or if a system A is in equilibrium, or it is in contact, it is in equilibrium with the B, then it is also, and B is in equilibrium with the C, then we can say C is also in equilibrium with the A. And it talks about the correlation of energy between the these three systems. So moving on to the first law. So first law it talks about the change of a internal energy of a molecule or a system with during the any chemical or a physical processes. And the second law, sir, is it's talk about the direction of energy flow and it talks about the randomness or the entropy that is produced during this energy flow during